Hi everyone. I'm Yang Yizhang, a PhD student in ID Lab Ghent University. And now I'm currently working on the receiver side of the Night LiDAR project. To understand what I've been doing, imagine that a self-driving car navigates through a foggy night. In conditions like that, the standard sensors are bright. So we need a more sophisticated way to sense the items, and that's where the FMCW LiDAR comes in. We will, instead of the process, we will emit church frequency, which the frequency will increase over the time. It will hit the target and reflect back, and we mix it with our local signal to generate a bit frequency, which corresponds to our distance and velocity information. And we need a circuit that translates the light into electricity. And that's where my PhD topic comes in, the years of the FMCW LiDAR, what is called TIA. And now is the time for the lab introduction. Welcome to the ID lab. Before we do the DC frequency or the transom measurement, we will use this microscope to examine the signal and the power supply connectivity of the EIC and the PIC. As you can see on the screen, the left side is the balance PD. It can mix the signal reflect back with the original signal to produce the bit frequency. And the right side is the 4-channel tolerant wave TIA. It can amplify the small input current to the large output voltage. It should be worth noting that here we use the wire bond to connect the power supply and also the input and output signal. And we also use the high quality capacitor to filter the noise bounce on some important power supply of the chip. In the FMCW LiDAR system, the TIA is the bottleneck. If TIA is not highly linear, it will create some harmonic frequency that the system will mistake for the ghost target. And if the TIA has a large noise, so we lose the ability to assess the faraway objects. And when the incoming signals varies in strength by order of magnitude, and what we call dynamic range, our TIA needs to maintain clear outputs without the clipping and the distortion. And to evaluate the transom response, we also set up an eye diagram measurement environment here. As you can see, this is the pole station. Since the wire bond will affect our high frequency performance, so we will use the probe to directly attach to the metal pads to characterize the high frequency response and also the transom response. And to do the eye diagram measurement, we will use the AWG. It is an arbitrary waveform generator. It can produce the PRBS signal, which then modulates the Mach-Zehnder modulator. And the light signal will pass through the optical fiber and then couple to the PD via the grating coupler. So when we enable the AWG, as you can see on the screen, you can get a 100 kbps per second NRZ signal. Notice that the width of the eye diagram converts the bandwidth of the TIA. The wider the width, the higher the bandwidth, and the which ensures the high velocity bit frequency we can capture. Yeah, and the transition age and the height of the eye diagram indicates how low the noise of the TIA is. The lower the noise, the clearer the eyes and the longer distance we can capture. And apart from the eye diagram measurement, we also have the level analyzer to capture the S parameter of the TIA. Yeah, and this is the lab introduction.